Hello everyone, this is Haley. Say hi. Oh, you can't say hi? Okay. Oh. Alright. So this is part 2. And this again is the material that will be used for November 10th, the class November 10th. And the main thing I want to go over here and cover is what happens to the Earth as it goes in its yearly path around the Sun. We already talked about in the last lesson that this is an elliptical orbit. Okay, an ellipse is an oval-shaped path, and this is exaggerated, by the way. You can see how oval it is. In real life, you wouldn't be able to distinguish that it was that oval. To you, it would look like a circle. Because Earth's orbit is only very slightly elliptical, right? In any case, what do we do next? Okay, so when Earth is in this position here, this is what we call aphelion. Okay, and you can see at this point in the Earth's path that it's much further from the Sun than this time of year. Okay, so the way you could remember that. The way you could remember that is the Earth is further apart from the Sun in this position. So aphelion, apart. Okay, the Earth is the furthest from the Sun in that location. And then half a year later, it's in this position here. And now it's pretty close. Perihelion. Pretty close. Perihelion. That was bad. But it helps you remember. So this is perihelion, and that's when the Earth is the closest to the Sun. Okay, so a couple of important things happen differently to the Earth when it's at these different positions. These are the extreme positions, you know, apart from the Sun and close to the Sun, but there are constant changes that are happening to the Earth as it goes around. By the way, I should clear up a misconception right away. Some people might be thinking that when the Earth is closer to the Sun, or when it's further from the Sun, that's what causes seasons. But it does not cause the seasons. This actually, the distance from the Sun, doesn't have a very significant effect on the seasons or the climate or the temperature of Earth. Okay, we're going to learn later on that there are other reasons why we have seasons, and it's not that. One thing you should know, though, and this actually was from today's lesson also, today being November 9th, and that is that the Sun will look a different size in the sky depending on what time of year it is. So when the Earth is here, the Sun is closer, right? And so I don't know if you can think of what that'll do to the size of the object. When an object is closer to you, like when Haley's really close to the camera, what happens to the size? It gets bigger. So that means that the Sun, at this time of year, the Sun is going to appear bigger in the sky. And we call that apparent diameter. It's not the true diameter of the Sun changing, of course. It's what appears to be true. Okay, and then half a year later, now it's further away, so it looks smaller. Okay, so yeah, so at this time of year, then the Earth will look smaller in the sky as it goes across. Okay, again, that's apparent diameter is what that's called. Let's move on. And so what's next? Let's see. Why do planets move around the Sun? Nothing really changed in this slide here. Okay. What changed? Oh, yeah. So the point that I want to go over is why is it that the planets do move around the Sun? And the truth of the matter is there are two forces that are acting on Earth to keep it in its orbit. One thing, the thing that's moving it forward is inertia. If you remember, we talked about Foucault, was that scientist who tried to prove the principle of inertia, and that is an object in motion continues in motion, flailing all around here, and an object at rest will stay at rest unless acted upon by some outside force. So the Earth, when the solar system was first forming, it was propelled, it was moved through space, and it will just keep on moving until, you know, unless something acts on it. And what acted on it in this case, the reason why it didn't just continue a straight line past the sun, is gravity. The gravitational force between, or the attraction between the sun and the Earth, that altered its path. Okay? And so it's a balancing act between inertia and the gravitational force of the sun that keeps it in this orbit. Okay? The inertia makes it want to go straight that way, but the sun is pulling it that way. And so that happens over and over again until it forms this path. Okay, so the things that I was saying before, that the important differences between these two positions of the Earth, for one, at aphelion, the Earth is moving slower, and the reason for that is that's the gravitational force between the Earth and the sun is weakest at that point. And the reason is because gravity is dependent on the distance between two objects. It's dependent on the size of the objects and how far apart they are. So the closer objects are together, the faster it moves. That's why the Earth moves faster when it's in this position, because it's closer to the sun. And then the other thing that determines gravity is the size of the objects. So the sun is a massive object, and so it provides a lot of gravitational force for us, for the Earth. Okay, so at aphelion, again, just to sum it up, the sun looks the smallest in the sky. The apparent diameter is the smallest. The gravity is weakest here, and the speed of Earth, which we call the orbital velocity, okay, it's the velocity or the speed through its orbit, it's the slowest there. Okay. What do you think? You learning all this? You gotta pay attention. Hey, over here. Okay. And then this time of year, during perihelion, the Earth is as closest to the sun, so the sun's gonna look the biggest in the sky. The gravitational attraction is the strongest, and the speed of the Earth, or the orbital velocity, is going to be greatest at that point. Let's see, what other things do I need to go over with you? Let me look at my notes here for a second. I got my laptop here to my left. That's what I've been leaning over to change slides every once in a while, but I also have my lesson plan book here. And let me see, we went over that, we did that. Okay, let me look at one of the slides I have here. Oh, it's you should note that the moon and its revolution around the Earth, its orbit around the Earth, it too follows an elliptical path, an oval-shaped path, and so it has the same similar type characteristics, where there's a moment when during the month when the moon is furthest away from the sun, from the Earth, and that's called apogee. Again, it helps the apart. And then when the moon is closest, it's called perigee. Okay? I don't know if the spelling there is correct. I'll have to check that. Okay, so the moon is furthest from the Earth. That's when the moon is going to look smallest in the sky. Again, the gravity is the weakest, and so the orbital velocity of the moon will be slowest in that position. And then half a year later, over here, you're learning it. I see it. No, you're going to sneeze. Okay. At this time of year, the moon is closest, so it's going to look bigger in the night sky, and the gravity is the strongest, and it's moving the fastest at that point. Okay? So it's really fast, and then as it moves, it slows down, slows down, slows down, then it starts speeding up, speeding up, speeding up, and then it slows down. Over and over again. Okay? What else? And that's it. Alright? That little mini lesson there should get you through the classwork tomorrow for November 10th. Okay, and I'll work on the next couple of lessons on YouTube for you for the 11th, and then oh wait, no, the 11th we have off, so Monday the 14th. I'll get that ready over the weekend. Okay, so definitely sometime Saturday or Sunday, make sure you watch the lesson for Monday the 14th, which I'll title it as Mr. Frampton's ES lesson November NOV 14. And again, my email, if you have any questions, is rframpton@schools.nyc.gov. Okay. See ya. Bye-bye. Bye.